G'day chemistry students. In this video, we're looking at dot points 5.4.1 and 3. This video is here to set up and introduce a lot of the fundamental key concepts for the last section of this module, which is all about solubility equilibrium. So today we're going to revise some of the ideas around dissociation, solubility, and solubility rules. Let's get into it. First off, I want to be looking at the idea of dissociation, and that is the concept of when something that can dissolve into water is put into water, the water molecules will surround some of those charged particles or particles that could become charged and grabs onto them and splits them up. And this is based on all sorts of bonding concepts which we would have looked at in Module 1. So as we're going through this animation, we can see that the water molecules surround the ionic substance here, breaking it apart and separating it. Now, looking really closely, what you should notice is the orientation of the water molecules as they pick up different substances. Now, this has got to do with some of the polar bonds in the water and the charges of the ionic substance itself. So remembering that here we'd have like the green would be a negatively charged particle and the white particles would be positively charged. Having a look at explaining this, it's got to do with the polarity of our bond in water. So I'm just going to look at this molecule here for the moment. Oxygen, we know, is really, really electronegative. And what that means is it's able to pull electrons towards it quite easily. The hydrogen, on the other hand, not so electronegative, doesn't mind having some of that electron density being pulled away. That means that the electrons in these covalent bonds hang around the oxygen molecule a little bit more. And that means that there's a partial, not a full, but a partial negative charge on the oxygen and partial positive charges on the hydrogens. And that dictates the way that the waters are orientated and also explains why those water molecules are able to actually be attracted to and pick up the ions that are a part of a salt crystal to begin with. So in the case of the anion, that would be a negatively charged ionic particle. We see that the hydrogens all orient towards and form an intermolecular bond between the anion and the water molecules. This intermolecular bond is an attractive force, and the water molecules are able to surround the particle and essentially pick it up and remove it from the lattice that it used to exist in when it was a solid. Same thing happens with the cations that are positively charged, this guy in the center, but they're being surrounded by the negative side of the water and the oxygen is oriented towards it. Now, not all salts are soluble. Many of them are insoluble, as our title suggests. And to explain the differences in solubility, what we need to be doing is comparing the strength of all of these intermolecular bonds that the waters can put onto an ionic substance and the strength of the ionic bonds which were holding the ions together and having it form a crystal or a solid as a result. So when we have intermolecular bonds, the bonds between the water and the ions, overcoming the strength of the ionic bonds, the bonds between the ions, what we can say is that substance is soluble. However, on the flip side, if we have an insoluble substance, what that means is that the ionic bonds between all of the ions are too strong, and the intermolecular bonds that the waters can put onto any of these individual ions are not strong enough to break up the ionic substance, which means that it stays soluble and means that we have a degree of insolubility. This is a very black and white version of explaining what happens when we're looking at solubility and insolubility. It's a lot more feasible to say that there is a spectrum of solubility. Some different salts are able to dissolve in water in different amounts and different capacities. That's actually kind of the whole point of this KSP topic in a lot of ways. But the solubility of a substance can be determined by how strong the ionic and intermolecular bonds are when you compare them to each other. The bigger the difference in the strength of those bonds, the more soluble or the more insoluble the substance will be. That leads to the formation of things like solubility curves. So what we'll see is at 0 degrees, all of these substances, all of these salts, have varying solubilities. Some are quite high, say approaching 100 grams in 100 grams of water. some quite low, less than 10 grams, dissolving into 100 grams of water at that 0 degree point. So what we can see is that all of those salts have differing solubilities. It's not just enough to say that they are soluble or they are insoluble. There are significantly greater differences there to go with that. But then also what we can see is that there is a temperature dependence on our solubility as well. And some salts are affected by temperature differences more than others. Again, a topic that we will go into in a lot more depth through the coming weeks. That then also means that we can start looking at our solubility rules and revising some of those. These rules began to dictate to us whether or not precipitation reactions would form. And certain pairings, certain groupings, certain ions generally tend to be more soluble ions or more insoluble ions. And depending on those combinations, you end up with this different spectrum of solubilities like we alluded to before. So there are our rules. We've seen them before. We might even apply them a little bit, but hopefully in this topic we can start explaining a little bit as to why those rules do exist. We can then start to look at this idea of precipitation reactions, as I said a second ago, and predict why something like silver chloride would be solid. So looking at silver nitrate, because all nitrates are soluble, this guy is going to be aqueous. Because the potassium here in potassium chloride is a group 1 metal, it also means that it's going to be soluble. However, this silver chloride, while most chlorides are soluble, as it says in Rule 3, silver chloride is an exception to the rule, meaning that if you have those ions put together, they're not going to be very soluble at all and end up forming a solid in water. The last one there is potassium nitrate. It's both has a group 1 ion and has a nitrate ion, meaning that it's definitely going to be a soluble substance. As I said, though, these solubility rules can be difficult to remember, and we're going to be looking at some techniques that we can use apart from just reading a solubility rule chart to be able to determine solubilities of substances and then predict outcomes of reactions and all sorts of stuff like that. Thank you very much, everyone. In the next video, we're going to be looking at some applications of solubility in a little bit more detail. In particular, we're going to be exploring how Australia's First Nations people, our Aboriginal and Torres Strait Islanders, have an understanding of solubility in their knowledge of the natural world and how that has been taken advantage of to increase food supply. But until the next lesson, have a good one.